In progress.
Okay, so here's our molecule of the day for today. It's Valium, which you probably have heard of before, or at least know something about. It's an anxiety drug. Your grandma might have a stash of it in the medicine cabinet somewhere. Um, but there's its skeletal structure. We've got 3 different rings, a few nitrogen atoms, an oxygen, and a chlorine, some double bonds, actually quite a few double bonds. So how does this structure look? Do we need any formal charges on any atoms? Nope. Everything's good as it is, unless I made a mistake, which I don't think I did. Um, One thing we could do is add lone pairs to atoms that get lone pairs, which is optional but can be very helpful. So actually, in this case, all of the atoms that are drawn explicitly have lone pairs, at least to some extent. What about the oxygen? How many does that have? Oxygen is neutral, 2 lone pairs. The nitrogens both have the same number of lone pairs. And what is that? One lone pair. And then the chlorine, these are probably the least important lone pairs, but the chlorine has 3. And so if you didn't remember that quite off the top of your head, that's okay. Just make sure you keep looking at that formal charge / lone pair chart that I think we talked about was it the first day? Either first day or last time. Okay, so let's do a quick rundown of the stuff that you do and don't include in skeletal structures. Okay, things that we do include, locking myself in here, but that's okay. Things that we do include obviously we have to have bond lines to show that the bonds are there. We include heteroatoms. And as a point of definition, a heteroatom is anything other than carbon or hydrogen. So I've never heard anybody call carbon and hydrogen homoatoms. Guess you could, but anything that's other than carbon or hydrogen is a heteroatom. So the heteroatoms in our structure there are chlorine, the nitrogens, and the oxygen. Everything else that's not drawn is either a carbon or a hydrogen. To include bond lines, heteroatoms, we also include hydrogens on heteroatoms. And assuming that this structure is drawn correctly and completely, which it is, that this tells us that there's no hydrogens on any of the heteroatoms that we've drawn there. So an example of a molecule that does have a hydrogen on a heteroatom is one that unfortunately is sometimes combined with Valium. You know what that structure is right there? Ethanol. It's not a recommendation that you should drink and take Valium at the same time. But there's ethanol. So we've got a heteroatom there, the oxygen. You can draw the lone pairs if you like. It's got a hydrogen on it, and we have to draw that hydrogen explicitly. We can't say, oh, we'll draw in the oxygen and we'll assume that the hydrogen is there. It doesn't work like that. You can't do that. Wrong. Bad. And then another thing we have to include in skeletal structures, not just skeletal structures, but any drawing or formula of any molecule ever in the history of time, is formal charges. You can never not write a formal charge. Fortunately, in this case, Valium does not have any formal charges. And the way we know that is because we just look at the structure. And because formal charges are always and forever required, you can instantly see if anything has a formal charge in the structure. Okay, things that we leave out in skeletal structures. Well, obviously, we don't draw the carbons. The carbon atoms in Valium are at each of the vertices, vertices, and at any terminus of a line. So there's actually only one case of a terminus here, and that's at the top of the nitrogen. So there's a carbon there with 3 hydrogens on it. So we emit carbons, and of course, we emit hydrogens on carbons, usually. The nice thing about skeletal structures is there's nothing that you're required to not draw. You can draw anything that's there, and it's legal. So sometimes we will draw hydrogens on carbon atoms. Couple cases, there's a few functional groups that we'll talk about, a few specific structures where it's traditional to draw a specific hydrogen, and we'll talk about that specifically. Or if it's a carbon that's near where a chemical reaction is taking place, just for bookkeeping purposes, it can be a good idea to draw that hydrogen explicitly so you don't forget that it's there, or you don't forget how many are on a specific carbon. And then another thing that we often omit, but I've broken this rule, is lone pairs. So we usually don't draw lone pairs. This one is even less of a rule than the hydrogens, because drawing lone pairs can be very good practice. And it generally is a good idea to draw them, but it's not wrong if you don't draw them. And of course, it's faster if you don't draw them. So if you're trying to do something really quick, no lone pairs. Of course, that means that you need to be able to look at a molecule and see where there's lone pairs if they're not drawn. We'll get there in a second. So let's go over, some of this is going to be review, some of this is going to be new. There's a couple rules for drawing skeletal structures. So I think we should know this one. Each corner or endpoint is a carbon. So one of the structures we used previously was this, which is hexane or N-hexane. In this case, the N just means normal, and so it's just a straight chain of carbon atoms. So we usually draw a zigzag, and then each corner or vertex is a carbon atom, and then every endpoint is also a carbon atom. Okay, I think we got that one. Rule 2, again, we talked about this, but hydrogens are usually omitted. So if we draw hexane like that, we can also, and this is a good exercise and something I'll ask you to do in the homework, is to draw out all of the hydrogens. Not the carbons, because we know that a carbon is always at a corner or endpoint. But for hexane here, we can draw out all of the hydrogens. So the yellow carbons at the end, how many hydrogens are on those? 3. Yeah. 1, 2, 3. 1, 2, 3. Carbon has to make 4 bonds. And so those carbons at the end in the original structure, right there, only have one other bond drawn to them. At least that's what it looks like. And so in order to have a total of 4 bonds, the remaining 3 have to come from somewhere, and that somewhere is going to be hydrogens. Okay, what about our 4 carbons in the middle? How many hydrogens do those have? 2. Again, each of those middle carbons in the plain skeletal structure have 2 bonds drawn to them. Carbon has to have 4 bonds, so the remaining 2 have to be to hydrogen. And so you, of course, you can go in and check your work and say, all right, for all the carbons in this structure on the right where I've drawn out all the hydrogens, do each of those carbons have 4 bonds? And now the answer is yes. Well, they had 4 bonds to begin with, but we weren't showing all of them. But now we're showing all of them, so we got the right number of hydrogens. And so another thing I'll ask you to do in the homework is come up with a molecular formula for this. And if you count it up, it should be C6H14. So another word we use to describe that 4 bonds is to say that carbon, when it's neutral at least, should be tetravalent. Tetra being 4. Okay, this rule I have been following, but I haven't explicitly told you about it. And that is, well, this really has to do with Vesper theory, and it sounds like Vesper theory. In Vesper theory, all the bonds are trying to stay as far away from each other as they can. And so when you're drawing skeletal structures, you should at least somewhat try to adhere to that. So I'm going to use an extreme example, and that is acetone. This is how we would normally draw acetone, but this is sort of not what you want to draw, because if we've got 3 things surrounding that central carbon, the furthest away that they can all be from each other is in this sort of triangle shape, and not him hanging upside down doing a split. Okay. Okay, another new rule. So for single bonds, the direction in which you draw the bonds doesn't matter. Initially, that doesn't sound like it really means anything or makes any sense, but let's take this molecule. This is exactly the same molecule as this. Okay, so what I've done here is taken the two CH3 groups at the end, just bent them down. And although you might think that molecule looks different, it can rotate sort of freely around these single bonds. And so the direction that you draw them in, whether they're left, right, or down, doesn't make a difference. So we could just as easily draw it like that, where one of them's going up, one of them's going down. Doesn't matter. Okay, we talked about this already, but heteroatoms and their hydrogens must be drawn. We have an oxygen like this. It's only got one bond on it, and it's neutral. It has to have that hydrogen explicitly drawn. Those hydrogens are not implied by the skeletal structure like the ones on the carbon atoms are. Okay, rule 6. This might be the most commonly broken one, or the most egregious one to break. And that is never give carbon more than 4 bonds. So that sounds easy enough, but like in a Lewis structure, I feel like when you're drawing Lewis structures, it's kind of hard to break this rule. But when you're drawing skeletal structures, for some reason, all of a sudden, everybody's brain just turns off, and then they end up drawing stuff like this. And I reserve the right to laugh at you if you do this, but all right, in this case, that carbon in the middle there has 5 bonds. 1, 2, 3 CH3 groups on the upper left, and then a double bond. So that's a total of, it's only 4 bonding domains, but that double bond is not okay. So that counts as 5 bonds, and that gives carbon 10 electrons rather than an octet, which it can't. No, impossible. Another culprit that tends to cause this issue is rings. So here, this carbon in the ring, there's 2 single bonds that make it part of that ring, and then 3 CH3 groups. That's a total of 5, and that is illegal. And then another case where it's sort of easy to mess up is this sort of carbon-oxygen double bond thing. It's easy to accidentally add 3 other groups to the carbon atom. That carbon in the middle there. has 5 bonds, 3 CH3 groups, and the double bond to the oxygen. So if you in the middle structure, I don't know, it kind of looks like a star, the carbon in the middle, and so sometimes we call these Texas carbons that have 5 bonds because they look like the Lone Star. I don't know, Matt.
When you get into resonance structures,
Yes.
I think that's like the easiest place to mess up putting more bonds on. Sometimes we take one off and we put something back on and we forget to get rid of the hydrogen.
That is true. When we start drawing arrows to show the movement of electrons, there may be cases where you kind of try to draw a bond forming that goes toward an atom that already has its octet of electrons, already has too many electrons, and so we'll talk about that when we get to resonance structures. But that's another spot where this rule can be broken. Okay, sorry, this is rule 7 out of 7, the last one. And that is, of course, always include your formal charges. Again, not just for skeletal structures, but for any chemical structure ever. So for example, this nitrogen has 4 bonds, and this is a classic example from the formal charge cheat sheet. That has to have a positive charge. You cannot draw the nitrogen with 4 bonds and no positive charge. That's always wrong. Okay, so speaking of formal charges, when you have heteroatoms like nitrogen or an oxygen, I think in these cases it's easier to see where a formal charge is or is not required. But what about carbon? Specifically carbons, when we don't draw the carbon out with the letter C, it's just an intersection of 2 lines. Mainly because for, let's see here, for a heteroatom, let's say for a heteroatom, you have to always draw hydrogens attached to the heteroatoms. And so you're always going to be able to see every single thing attached to the heteroatom. But with a carbon, we don't always see all of those hydrogens. And so this can get confusing. I think you'll see here. So the nice thing about carbon is that carbon has a formal charge when it has 3 total bonds. In fact, this is the case with a negative formal charge and a positive formal charge. So that makes it a little bit easier. So if you've got a carbon with 3 total bonds, you have a formal charge. Now, this isn't 3 bonds to other carbon atoms, it's 3 bonds total. And so this is another reason why you always have to include formal charges, because otherwise you're not going to know how many hydrogens are on that carbon. So if we have 3 bonds with a lone pair, that's a negative formal charge. Three bonds without a lone pair, is a positive charge. So if we just draw this structure by itself with no formal charges on it, how many hydrogens are on the central carbon? One. Because there's 3 carbons on the outside that all have a bond to the central carbon, so that's 3. But for neutral carbon, we got to have 4 bonds, and so one of them has to be to hydrogen. Can apply the same thing to this structure. The carbon in the middle now only has 2 bonds to other carbons, and if it's neutral, which it is in this drawing, it has to have 2 hydrogens. So I know we're just talking about neutral carbon here, but okay, so now let's say that we have that same thing, but we have a lone pair on that carbon and we have a negative formal charge. When carbon has a formal charge, it has 3 bonds total, not 4. Okay. So there's 2 bonds explicitly drawn. Those are to carbons. How many hydrogens do we have on this negatively charged carbon to get to 3 bonds total? Just 1. So this is called a carbanion because it's negatively charged. That's an anion, and it's carbon, so it's a carbanion. Really creative. Right? Okay. So now we have a positive charge with no lone pair. And this is actually the same thing. I mean, not really, but it's still going to have 1 hydrogen because a carbon with a formal charge only has 3 bonds. So that central carbon has 1 hydrogen. Something that's positively charged is a cation. So this is a carbocation, not a carbocation. Okay, if this seems a little weird, that's okay. We're going to get to this March-ish when we start talking about some more reactions. And so you can kind of file this away at least for a little bit. But it's important to be able to see the absence or presence of those hydrogens when you've got charges on a carbon atom. Okay. So again, we did this at the beginning with our practice on Valium, but lone pairs on heteroatoms in skeletal structures, these are optional. Good practice to draw, but optional. And so because they're optional, you need to be able to fill them in when they're missing. So again, your formal charge cheat sheet is also sort of a lone pair cheat sheet as well. So here's some structures that have heteroatoms in them. So how many lone pairs do we need on the heteroatoms here? What about the oxygen? 2. Nitrogen? 1. Fluorine? 3. Weird, but the least important one because they're often not super involved in reactions. And sulfur? Now, sulfur is just big oxygen. So you can redraw the structure, substitute it with oxygen. Okay, so now that oxygen has 2 lone pairs, and so the sulfur is just going to be the same, 2 lone pairs. Again, this is something that you should probably memorize, but if push comes to shove and you can't remember, look at the number of bonds and then look at the periodic table. Where is the element in the periodic table? If something like oxygen is in group 6, it's got to have 6 valence electrons, has 2 bonds, and so the rest of the valence electrons have to come from lone pairs. Generally speaking, the more bonds something has, the fewer lone pairs it's going to have. So we've talked about condensed structures, CH3, CH2, 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 CH3, etc. And we've talked about skeletal structures, but in reality, what we often do is, at least to some extent, combine the two. This is most common with like methyl groups or CH3 groups. So let's take this structure here. What a lot of chemists will do is, rather than include that line on the right-hand side, which could be interpreted as a stray mark, or even worse, a negative charge on the oxygen. Oxygens often have negative charges. And so if you didn't draw it at that angle, maybe it would look like a negative charge that you didn't circle. So there's some people that argue that you should always do it the second way, which is to draw out the CH3. I don't really care. But the main thing here to see is that, so this sort of side of the molecule we've drawn as a skeletal structure. And we've written the CH3 sort of like a condensed structure, and that's totally okay. You can actually take this a step further, and there's another CH3 group in this molecule on the right, the left-hand side of the right. There. And so if you want to be more explicit about exactly what the end of that line is, you can also write out the CH3 group like it's a condensed structure. But The thing here is because it's on the left-hand side, we have to show that this bond in blue is from a carbon to another carbon. So we have to draw that carbon of the CH3 group right there. We can't leave it like this because we've drawn out the carbon explicitly. And so that means we have to draw out the hydrogens explicitly. And so we just put them over there. So it becomes H3C instead of CH3. Means the same thing, but we draw it backwards. To show the correct connectivity between the carbon here and the carbon there. Same thing goes for an OH group. If that's on the left-hand side of the molecule, then it also needs to be drawn backwards to show that the bond here is between the oxygen and the carbon rather than the hydrogen. Okay. Okay, give this one a shot. So see if you can give me a skeletal structure of that molecule. There's like a bazillion correct answers. So make sure you look at your rules and then the chart of things to include versus things you don't necessarily have to include. Here's a couple different ways that you could do this. Personally, the one that I would draw is the first one here, but again, as I said, there's a bazillion correct answers. So the main thing that you want to look for is there's two carbons in the molecule. And so you got to have two carbons and only two carbons in your structure. So for example, in these cases over here on the right, we've got the oxygen atom. There's a carbon at that intersection there, and there's a carbon at the end of the line. On this one, I've drawn it out explicitly as a CH3, and that's okay as well. You'll notice that in some of the cases, I wrote the OH like right together, the oxygen and the hydrogen. And in some other cases, I drew out the bond between the oxygen and the hydrogen. That's also optional. What else? I included the lone pair on 3, but not all of the structures. That's okay. The one at the top right doesn't have the lone pair. That's fine. You don't have to include the lone pair. So there's, what else? Oh, you can rotate or flip any of them at will, and they're all still correct. So I don't know, there's like 64 or 128 correct answers for this. If you're not sure if yours is correct, feel free to show it to me and I'll judge you as nicely as I can. Okay. Another one to practice on your own. No. Whoa. Oh no, that's correct. Sorry. That one should be fun. That tripped me up as I was writing it. So that one's a little trickier, but okay. So what we've talked about so far is kind of organic chemistry is like kind of like learning a language. And so what we've learned up to this point is how to draw the letters and draw that. See, this analogy always falls apart at some point. But essentially, that's the foundation just of drawing the molecules. But in order to talk about the molecules, so like to form sentences in the language, or whatever, we have to be able to specify individual parts of the molecule and say, oh, okay, I'm talking about, this atom or that atom without, referring to it by like pointing to it in a drawing or something like that. And so the way that we do that is with functional groups. So a functional group is a part of a molecule predictable with predictable reactivity or predictable functionality, hence functional. And so one of the reasons that we went through all this business with skeletal structures is that they help us see functional groups, structures So sometimes we'll call functional groups FGs in writing. And that this will make more sense with an example, I think. So let's say we have this molecule. What's the most interesting part of that molecule? Is it the carbons on the end? No, it's the double bond, right? That's like the only thing that's there, other than just a bunch of random carbons. So this double bond is a type of functional group. Specifically, it's called an alkene. We'll get to those specific functional groups in a moment, but okay, so we can now name that particular area of the molecule. That's convenient. But also, if we do a chemical reaction with something, in this case, molecular hydrogen, and some palladium metal as a catalyst. Look at this, we're finally doing actual chemistry. That's the product of this reaction. And you can immediately, without having to draw Lewis structure and count atoms and lone pairs and bonds and all this stuff, you can immediately see what the change is, right? The double bond is gone. In fact, specifically, we've just added those two hydrogens from the H2 to each of those two carbons, but we'll get to that in a little bit. Months, a little bit. So it immediately tells us that there's been a change, and we can see where the change is. So this schematic is good for fairly small molecules like this, but what if we have a molecule of DNA or a protein or some giant molecule? Even then, a skeletal structure, which at this point is like super abbreviated, right? A skeletal structure is still going to be way too large. And while it will look cool if you draw it all out, it's not practical for large, really large molecules. And so to abbreviate things even more, we're going to use what we call R groups. And an R group is a variable atom, or more commonly, multiple atoms, attached to a core structure. So in the same way that the functional groups are the interesting or the reactive parts of a molecule, R groups are like the opposite. They're the stuff we don't care about. And the stuff that would be really nice if we just didn't have to draw it and we just put the letter R instead. So that's what we're going to do. Let's take our example molecule, our example alkene. And okay, so the double bond on the right-hand side, we're interested in that because that's going to do our chemical reaction. But what about this cluster of atoms on the left? If we look at our reaction, those three carbons on the left are not affected in the reaction. Again, in order to select what we're going to make into an R group, you kind of have to know this in advance, but we'll get to that later. So we can actually just hide. This is like hiding a column in Excel. We don't want to see it. We don't care about it, but it still needs to be there. And so we're just going to replace this functional group, which, by the way, is called an isopropyl group. You'll notice I made a Freudian slip and I called it a functional group. In this case, I mean, we'll call these small collections of carbon atoms functional groups, even though they don't really do anything. So I apologize for that. But so this isopropyl group, we don't care about it. And so we're just going to make it into an R group. So we're just going to put R. in place of those 3 carbon atoms. We can leave that as is. Sorry. We can leave that as is and just say, okay, that's our molecule. R is something else. We don't care about it. Don't worry. That can be kind of dangerous sometimes, because what if R is actually reactive or has like interesting functional groups in it? Or we can specify and say, hey, R is equal to isopropyl, or we could make a list of a whole different set of things that R could be. And that way we can describe an entire set of similar molecules more efficiently. We'll do that in organic too. So an R group, the R actually stands for radical, but I think it's easier to remember that it stands for the rest of the molecule. R for the rest of the molecule. So functional groups are important and we care about them a lot. R groups, we don't care about them, so we just don't draw them. And so, of course, this puts your focus on the interesting or the reactive functional groups. So let me give you a couple examples of different ways that we can draw molecules. Okay, so let's take this one. Again, sharpen up your hexagon drawing skills, because we're going to do a lot of them. So this molecule has 3 different functional groups in it. This ring with the 3 double bonds inside it is called a phenyl group. And it has actually a specific abbreviation. I'm going to give you a chart of these in a second, so don't worry too much. So that's a phenyl group. This one is called a ketone. And an OH is an alcohol. These are just a couple examples. But now I'm gonna take our molecule and I'm gonna rewrite it in a variety of different ways, using a combination of the skeletal structure as it's drawn, R groups maybe, and the abbreviations that we often see, like the pH for phenyl. So we could draw it like this. Draw it like that. We could draw it like that. Could draw it like that. And I could keep going and going and going. But the main thing I want to get across to you here is, well, first of all, there's a bazillion, and I didn't even try to do a condensed structure, which I could do. But there's a bazillion different ways to draw the same molecule. And also, maybe even more importantly, these give different levels of information about the molecule. So the clearest one is the first one, because there's no R group. Everything is drawn out explicitly. The only thing that I've done differently is instead of drawing the six-membered ring, the hexagon, that's the phenyl group, I just use its abbreviation, pH. So there's no ambiguity in that structure as to what we're talking about. It's just been slightly abbreviated. In the second structure, we've still got the left half of the molecule is explicit. The phenyl group, we know exactly what that is, and the carbon double bond oxygen. But then this carbon to the right, all of that, what I'm basically saying by calling that an R group is that's not important. We're not talking about it right now. Let's just ignore it. So that's a correct representation of that molecule. Or an infinite number of other molecules that have something attached, something different attached where the R is, like an amino acid or anything, sulfur. Who knows? Same goes for the third and the fourth structures. The third one, okay, in this case, now we're essentially what we're saying by drawing this structure is, okay, the right side of the molecule is what's important to us. The phenyl group doesn't matter. So it could be a phenyl group, it could be a phenyl group where we've, attached something to one of these carbons and so on and so forth. And then, of course, the last example, that's showing that in addition to knowing about the phenyl group and the carbon-oxygen double bond, we also care about those two carbon atoms. And then the OH, the alcohol, is not important. It could be something else as well. So it's just an overview of the different ways we can draw molecules. Okay, so on Blackboard, and if you happen to have a device handy, I would recommend bringing this up. It's on the front page. It's like the third or fourth thing. And it's just a chart of a whole bunch of different functional groups. So a couple of these we have already seen. I think I showed you the isopropyl group. And so the most basic way to show any molecule that has an isopropyl group on it is by calling the entire rest of the molecule R. And then this that we've explicitly drawn is the isopropyl group, is the actual functional group. So that's how all of these are shown. The functional group is everything attached to the R. So kind of the first set that all go together is this. These are all alkanes. And an alkane is any sp3 hybridized carbon, so that's a carbon with 4 bonds, that doesn't have any real functional groups attached to it. Now, when I say that, I'm talking about functional groups that have double bonds or have heteroatoms. Generally speaking, the alkanes are sort of like the functional groups that aren't very functional. And so they're kind of their own little class, but they're still important to know. Specifically, for example, a methyl group, right? These are just the carbon atoms on the ends of chains. So anything where there's maybe a long straight chain of carbon atoms, the carbon at the end, that's a methyl group. So it's a functional group, but it's not particularly reactive. And so often we abbreviate it, and we do that just by writing Me for methyl. So in hexane, which is that, let's say we're focused on this carbon atom at the end. We can also write this structure as that with a CH3 at the end. Or we can use this abbreviation for a methyl group Me. And yes, these intentionally are made to look like element symbols. PR is praseodymium, I think, but you don't see that in organic chemistry, so there's generally no confusion. There's some others that are actually the same as real elements, but that never ends up being much of an issue. So there's some various alkyl groups. Methyl is 1 carbon, ethyl is 2 carbons. There's 2 different kinds of propyl groups, a straight chain one and the isopropyl group, same number of carbons, just a different attachment to the rest of the molecule. Then these 4 down here are butyl groups, which are all 4 carbon groups. And there's, with more carbons, there's more ways to attach them. There's pentyl groups that are 5, hexyl groups that are 6, but that tends to get pretty complicated pretty quickly. So that's just a overview of the alkanes. Some more interesting functional groups that have double bonds or multiple bonds or heteroatoms. We saw this one previously, but an alkene, also called an olefin. The main feature here is the carbon-carbon double bond. So an alkene is any carbon-carbon double bond with various different things attached to it, generally carbon atoms or hydrogens. An alkyne, so we're changing the that vowel right there, and that changes the whole molecule. An alkyne is a carbon-carbon triple bond. Phenyl group we saw, and then some other very important ones. Alkyl halides are literally just anything with the halogen on it. It's that simple. We just call that an alkyl halide. An alcohol has an OH group. There are some molecules that have the OH group in them that aren't specifically alcohols. We'll talk about those in a bit. Then some other ones with oxygen, ethers, peroxides, and epoxides. Epoxides are cool because it's a 3-membered ring with oxygen in it. Nitrogen, when it has only single bonds, is called an amine. You'll notice I have primary, secondary, and then in the next column, tertiary and quaternary. We'll talk about those distinctions in a little bit. Well, next time, probably. Anything with thio in it has to do with sulfur. And because sulfur is right below oxygen in the periodic table, these tend to behave just like, well, not just like, but fairly similarly to oxygen. Then we've got the next big, the next big category. And this is, one that all sort of goes together. It's these. These are all variations of the carbonyl group. And a carbonyl group is just a C double bond oxygen. These are extremely common. They're everywhere. Carbon-oxygen bonds are really strong. And they also make the parts of the molecule around them more reactive. So they're stable and reactive, which is something particularly interesting to chemists. So here's a large variety of different types of carbonyls. Aldehydes have one R group and a hydrogen on them. And you'll notice over here on the right, we've got some various abbreviations, generally all starting with CO, which indicates the carbon-oxygen double bond. Ketones, carboxylic acid, and the list just keeps going on and on. Then after that, there's a couple unique ones that involve nitrogen, the nitrile or cyano group, which is a carbon triple bond nitrogen, and then the ever explosive nitro group with those interesting formal charges on them. So one thing we'll do in the coming classes is we're going to see a lot of examples of functional groups like this actually in molecules. So I know just the general form thing they're pretty vague, which is intentional because you can have these functional groups in a wide variety of molecules. Yes. Oh my God, it's already the 21st of January. Sorry. Keep that chart up if you have it on your phone, because we're going to do a little practice here with identifying. Okay. Okay, so look at your chart and see how many of those structures you can identify. I'll actually give you, I'll give you this one first. So, okay. So here, this is kind of how you would go about doing something like this. Okay, so we've got an oxygen atom. Okay, and it's attached to two things. And those things are just carbon atoms, and then the whole rest of the molecule is attached to them. So let's call those both R groups. And now we have a general form for that functional group. Then you go look on your chart and you find that this is called an a ketone has a carbon oxygen double bond. This is an ether. Yes, the same stuff that you soak a rag with and knock somebody out. So there's 1, 2, 3, 4, 5 other ones.
There's a carbonyl group.
Yes, there is. Yep, there's a car. Yes. So this is a carbonyl group. Specifically, what kind of carbonyl is it? There's two R's next to it. And so that is a ketone. So a carbonyl, specifically a ketone. We have a halogen over here. There's that pH, which we've seen before. A double bond. And then what about this ME? So when we're looking for functional groups, you're just looking for stuff that isn't just plain lines. Anything remotely interesting, generally speaking, is a functional group. So the bromine there, that's an alkyl halide or a haloalkane, if you like. The pH, we talked about that one, that's a phenyl group. The carbon-carbon double bond, what's that one? Alkene. And Me, methyl. Another thing to notice with regards to methyl groups is, surprise, there's another methyl group right there, because any end of a line is a carbon with 3 hydrogens. Any carbon with 3 hydrogens is a methyl group. So any end of a line is a methyl group. Generally speaking, I won't ask you to label methyl groups because they tend to be everywhere all the time. But questions on IDing functional groups. For this, you just have to practice it a bazillion times. Yes.
The carbonyl group
Yes.
has like dotted lines. Is that just saying that like it's backwards? So it's the only one.
Yeah. So that's just saying that I didn't want to put R there because the stuff on either side of the carbonyl group is pretty specific to the individual like subtype. So let's see. In all of these cases, R generally is a carbon atom based type of thing. Can be exceptions to that. But those two dotted lines essentially mean that it could be anything, any sort of atom on either side of the CO. Now it's kind of not super clear, but I think with some practice, it will start to make a little more sense. Okay, see you on Monday, right? Yes.